Professor Steve and Gus is back with another problem of Chem Exam 3. Today, we'll be doing question 20. What volume of oxygen at 24 degrees Celsius and 0.88 atm is needed to completely react to VI combustion with 48 grams of methane gas? Whoa, that's a lot. So this is just a combination of chapter 6 and chapter 4, I think. I think chapter 4 was stoichiometry. Yeah, chapter 6 and chapter 4. So, oxygen gases react with methane in combustion. So let's go ahead and write the combustion reaction. Methane is CH4. And it's a gas, as stated. Plus oxygen gas equals H2O plus carbon dioxide. And carbon dioxide's a gas, and H2O is a liquid, I believe. I believe actually during combustion, since combustion is so hot, the hydrogen H2O would instantly become gas, or not almost instantly. But without the heat, I believe it just becomes regular water. Anyway, just cool tidbit. Oh, well, first of all, Gus, you might notice something quite obvious. There's 4 hydrogens on this side, only 2 on this side. So we need to balance the equation. To balance this, let's start with balancing this side. Let's try to balance hydrogen first, because since O2 is alone, it's gonna be way easier to balance carbon and hydrogen first, and then worry about oxygen. So we now have 4 hydrogens on the left side, 4 hydrogens on the left side. I mean the right side, sorry. We have 1 carbon on one side and 1 carbon on the other side. Now, all that's left is to balance oxygen. So we have 2 oxygens on this side, 1, 2 oxygens on the right side, and plus 2. So there's 4 oxygens on the right side and only 2 on the left side. So we need 2 more oxygens on this side, which is easy. So now there's 4 oxygens total on both sides. We have our balanced equation. Sorry again, do people keep walking by, so I look away for a second. They've walked by like 6 times now. It's crazy. And let's look at the equation. The problem. What volume of oxygen at 24 degrees Celsius and 0.88 atm is needed to completely react with VI combustion with 48 grams of methane gas. So first of all, we're looking for how much oxygen is used in this. So So we need to know how much oxygen is used reacting with 48 grams of methane gas. So let's convert methane to moles first. Oh man, I don't know how to write this. 48 grams methane. And per 1 mole of methane is 16.04 grams of methane as well. Yeah. Because 1 carbon is 12.01, hydrogen is basically 1, so 12 plus 4 is 16. It's about that. And now we have moles of methane, and we want to know how many moles of oxygen we're using, because that's what the original equation is asking. What's the volume of oxygen? So of course we need how many moles of oxygen is needed. So let's look at our equation. Per 1 mole of methane, there is going to be needed 2 moles of oxygen. So double the amount of moles of methane is used. So per 2 mole of oxygen gas, 1 mole of methane. Let me see that. And I was going to do that. So 45 divided by 16.04 times 2 is this number, 5.611 moles of O2 gas. Making sure I did it right. Sorry. Yep, probably. Anyway. So the original question was asking what volume of oxygen is needed. So we look at the gas formula we use for like everything. P times V is equal to N times R times T. And it's asking for volume of oxygen. So we can divide those sides by P. And P's on the left side cancel out, even though it's just V equals N times R times T divided by P. And this would give us our volume of oxygen. Now let's look at all our variables. We're looking for V, so I'm gonna erase this real quick. So I have room. Hope you don't mind. Hope you wrote it down, Gus. Should have asked first, but oh well. Should have been faster, Gus. You are an eagle. I'll leave that there. So we don't know our V yet. So I'm gonna write V is something. We know our moles, because that's what I just found. There's 5.6111 moles of O2. R is universal gas constant, so 0.0821 liters ATM divided by moles Kelvin. Temperature is. Our temperature is 24 degrees Celsius. However, we need it in Kelvin, so our units cancel out at the end. So we're going to ahead and convert 24 degrees Celsius to Kelvin. So we add 240 to get to Kelvin. We add 273. So 24 plus 273 is 297 degrees Kelvin. Or if you know that at room temperature, Kelvin is 298. It's 298 degrees Kelvin at room temperature. And we know that this is just 1 degree lower than the room temperature at Celsius. You could have just took a guess. There's not 297. Doesn't matter. Also last thing. Oh yeah, pressure. And pressure is 0.88 ATM. And I'm gonna get close real quick. I hate when I do this. Make sure you can read it. Probably. Sorry, I don't know if I've said this before, but for some reason when I'm viewing it, when it's recording, it's flipped. But afterwards, I can do it just fine. So if you can't read something, I can't tell because I can't read it no matter what. Anyway, so we found N and we have all our given units. So let's plug all our units into the formula. So 5.611 moles. Oh, I'm going to do this over here so we have more room. So 0. Oh, what was it? Sorry. So our moles is 5.611 moles of O2 times universal gas constant of 0.0821 liters ATM, and that is divided by mole times Kelvin, and then we multiply top by T, which is 297 degrees Kelvin, and then this is all divided by 0.88 ATM, which is our pressure. Yep. So let's cancel out our units. Moles cancel out. Kelvin cancels out. ATM cancels out. And all we're left with is O2 liters. So plug everything in there. Oh, from my calculator. And this will equal to 165.5 liters of oxygen gas. Sorry, to people walking by. Sorry if you hear it. And that is the volume of oxygen. If you don't believe me, we can check real quick by plugging our numbers back into P times V equals N times R times T. You remember that? Yeah. So 155 times 0.88. I won't use exact numbers because I don't really feel like it. Just because we're just checking our work. We've already solved the answer. I'm just using semi-accurate numbers. And this will give you 136.84 liters ATM, whatever. So that is equal to N times R times T. So 297 times 0.0821 times 5.611. And that gives you like 136.8. Just basically the same thing. It's only off because I didn't use exact numbers for proof. So as you can see, that's our volume. So just say it again, Gus. What is the volume of oxygen at blah blah blah? And that's the volume of oxygen. You have a good day. I don't know who ever watches these videos, to be honest. So I don't know if they force some TA to watch these. Regardless, I appreciate it. You have a blessed day or blessed night whenever you're reading this. Blessed life.